Okay, I guess we'll get started now. Today, my plan is to talk about support vector machines, kernels, and then a bit on Lagrange multipliers, which is part of an extra, we made an extra credit on the homework, but I think it's a useful skill to know. Okay, so we'll start with support vector machines, which solve a general problem of classification, which, as I'm sure you're intimately familiar with by now, is when you have a discrete label that you want to predict. So say for support vector machines, you might have points. Some are labeled positive, some are labeled negative, and you somehow want to be able to predict kind of the general, let me make a better picture, a general rule that you can use in order to predict future points that you get. So in this case, if we wanted to draw a linear decision boundary, there are several that we could draw. One might look like that. So you can see we have all the positive points on one side and all the negative points on another side. That's not the only decision boundary we could draw. We could also have one that looked more like this. So of the two, the dashed line and the solid line, does anyone have any particular attachment to one over the other? Do you think one would be a better boundary to have than the other? Yeah, the solid one, right? So what's the intuition behind why the solid one is maybe a better decision boundary? Yeah, so that's getting into the idea of margin, but really another way, a similar perspective on that is that you can see there are some points that are pretty close to the boundary. So what if we were to move this point just a little tiny bit over here? It seems like it's pretty similar, but if we use this original dashed line as our boundary, then all of a sudden we're predicting that it's the totally opposite label. So in that sense, if you have this large margin idea, it's a bit more stable to if your data is moved around slightly. So that's kind of why we would prefer a line like the solid one here. So like you, what is your name?
Sean.
Sorry, what?
Sean.
Sean? Okay. So like Sean mentioned, the idea here, you have a larger margin in that it's sort of like the distance from your points to the decision boundary. You want to kind of like maximally separate the points on one class from the other. So in this formulation, kind of where SVM gets its name, is that the points that lie on this boundary, maybe you have a couple others, are called support vectors. And the idea is that the classification, the results of your classification, really hinges only on the values of these support vectors. So over here, provided everything's all negative, we could have a point here, over here, over here. It really doesn't matter. The only thing that we need to keep track of in order to maintain our solution is, in this case, just 3 values. So maybe you have thousands and thousands of points, but only 10 or so are support vectors. So really don't have to, it doesn't depend on as many data points. And so we can represent this decision boundary mathematically by specifying a value for this particular line. We'll say it's W transpose X plus B equals 0. So in lecture, when Nina went through, she assumed that everything was centered. So essentially you had B equals 0. But you can also do this kind of slightly more generally, where you just sort of shift your data, and B can be non-zero. And then the way you predict a value is that you say, so let's say this minus has a class labeled -1, and the plus has class labeled +1. Then the way you're going to predict that value is everything that's on the negative side here satisfies W transpose X minus B is less than -1. And here on this side, you have W transpose X plus B is greater than 1. So now if we get a new point, or greater than or equal to. So now if we get a new point, say maybe we have a point like right here that we get. If we already know W and B, and then of course we know the coordinates of the point, oops, we have a point right here. Don't know what it is yet. But we know W, we know B, we just make this calculation. So maybe here we say W transpose X plus B equals 2, which is greater than 1, so we're going to say that this point is positive. And then suppose we have a point all the way out here, and we want to guess, make a prediction of what its label is. So here again we're going to, oh sorry, that should be a plus. We're going to calculate W transpose X plus B, and say here maybe it equals negative 15. And so since it's less than negative 1, we're going to say that this point is negative 1. It's class negative. And so here you can kind of get a sense that this was sort of close to the margin and the value was 2. This was farther away from the margin and the value was negative 15. So the magnitude here kind of indicates the confidence we have in this particular prediction. Yeah, so our final prediction rule is just the sign of W transpose X plus B. Yeah?
So in between the two parallel lines, it's like between the
Yeah. So here, if it's exactly on this line, it would be 0. Here is positive 1, here is negative 1. So right now, this was just talking about the hard margin formulation of SVM, where you say that nothing can be in the margin at all. Everything has to be linearly separable, and nothing can be in the margin. So in that case, that's enforced on your training data, but when your test data come in, you don't know, like you didn't know what the values were as you were learning your W and B parameters. So really, you can't really say there. So because otherwise, like, I mean, I guess you could say if something's in here, like, oh, I'm not really sure. But if you just want to still get a guess for what the value is, if you just do the sign, then you can still get a value for your predicted value of y, even if it is in the margin. Yeah, so this was just assuming we already know the W and B parameters, but really what we're interested in if we have a data set is we want to find these values. So we can set it up as an optimization problem, like we talked about in class. So if we say that this distance here is the margin, and we'll call it gamma, the margin. That's inversely proportional to the norm of this vector W. So we want to maximize gamma here while obeying these constraints that all of our negative points are on one side of the margin and all of our positive points are on the other side of the margin. Does this one not? No, it doesn't go up. Okay. So our optimization problem here is going to be, we want to maximize gamma subject to, first of all, when let's say our inputs are x and the label is y. Say x is n-dimensional and each y is -1 or +1. So we want to obey the constraint that W transpose xi plus b is less than -1 for all I such that it's in the negative class, and then it's greater than +1 when it's a positive value. And we can combine these two constraints by saying that yi times W transpose xi plus beta is greater than or equal to 1. Because in the case that, in this setting, when yi is -1, you'll have, if you multiply both sides by -1, you'll get yi times this value here, and then you'll have 1 on this side, and then you'll flip the direction of the inequality. And then over here, if yi is +1, you have yi times this greater than or equal to 1 still. So we can combine the two of them. And this objective here, that's equivalent to minimizing the norm of W, and we'll just square that like Nina mentioned in class to make it computationally efficient, or possible even. So is that hard to see over there? Yeah?
I can't see what's behind the root. I guess it's a -1 on top.
Oh, sorry, yeah. So this is, this constraint here is the idea that all of these negative points are on this side of this line here that was specified by W transpose x plus b is less than or equal to -1. So yeah, that's for all of your negative points. And then the second one is for all of the positive points. I think this is on the lecture slide, so you can find it there if you can't see it here.
Yeah.
But yeah. And so this one just combines the two into a single constraint, because then also you're not like separating your data according to what the label is. So far we are all, we've been considering the case where it actually is linearly separable, so it is possible to draw this decision boundary between the two classes and perfectly classify everything. If it's not linearly separable, there are a few different things you can do. First of all, suppose the data set looks something like this. So it's just right here that I've circled. In that case, you can't draw a line to separate the two classes. But suppose we did some sort of transformation, we'll call it phi of x, and such that then we transformed it and it looked more like this, kind of like more like a quadratic. Then you see we can draw that line there and continue. So we kind of get more into talking about these transformations and stuff later on when we get to discussing kernels. So for now, we'll talk about still just standard SVM, but the non-linearly separable case where we relax the constraint that things have to be absolutely on one side or the other of the margin, and on the correct side too. So now we're going to look at the case where maybe we have like a point here inside the margin, we have a point over here that's misclassified entirely, and then, you know, another one over here that's misclassified too. So again, this is the decision boundary. So now you can see we have things in the margin and things that are misclassified, and we're going to reformulate the way we set up this problem so that we can still find it. So if we had this data set here and tried to solve this problem, we wouldn't be able to find a solution because a point like this one is going to not obey this constraint here, because you can see it actually is a negative label, but because of where x is positioned, this value is going to be positive. So this would be -1, that would be +1, this entire value here would be -1, which isn't greater than or equal to 1. So we wouldn't even be able to find a solution at all. So we're going to change our, the way we've set up this optimization problem so that we can still find a solution even if the data aren't linearly separable. So this new formulation is called soft margin SVM. And I guess I'll write it in here. So the way we're going to handle this case is we're going to kind of look at maybe how wrong a point is. Because if you remember, when we were making these predictions, kind of the value, the magnitude of this value here indicated how confident we were in our particular prediction. So maybe we can take that in the other direction, and if it's, you know, just a little bit wrong, only count it as a slight penalty. So the idea behind the soft margin SVM, our new optimization problem, we're going to want to minimize, as before, this value, the norm of w squared. But then we're going to add in a penalty on these slack variables, psi, that indicate just how wrong a prediction might be. So if we go through and draw an example, again, suppose, let's see, we had plus on this side, and then some minus over here. Let's say maybe this was our decision boundary. We had, like, this is one margin, this is the other side of the margin. So you can see here, like, we have that value's in the margin. Maybe we have this value over here that's misclassified. Yeah, we'll have this misclassified over here too. So the way we can relate these slack variables to where the points lie is that if something is on the correct side of the margin, completely correctly classified, it would have a slack variable value of 0. So like this point here, it's on the proper side of the, well, first of all, it's on the correct side of the decision boundary, so it'll be correctly classified. It's also farther away from the margin. So it's going to have a value of 0 for its slack variable. If we have something like this over here that's incorrectly classified, it's going to have a slack variable value that's greater than 1. However, if we have something that, like this one, it's still correctly classified, but it is in the margin. Here, its slack variable value is going to be between 0 and 1. So you can see we don't have as big a penalty on something that's maybe just in the margin but still correctly classified as we would with something that's on the other side of this decision boundary and incorrectly classified. So that's how these slack variables relate to where exactly the points lie. And here our constraints are going to be, again, well, not again, but we're going to have the same one combining the relationship between our prediction and the true value. But now instead of saying it has to be greater than 1, we're going to say it has to be greater than or equal to 1 minus the slack variable value for that particular point. And then these slack variable values are always greater than 0. So these are both for all I. Does everyone follow this part? Okay, so yeah, the idea is that instead of strictly enforcing that everything has to be on one side or the other of the margin, we're going to allow things not to be. But the fact that we're adding this penalty, these are all non-negative, so this is going to be a positive or non-negative penalty that we're adding to something we want to minimize. So we want to keep this low, but at the same time trade that off with how big we can make the margin. Because as we increase the size of the margin, like that will increase W, because remember the margin is inversely proportional to the norm of W. So if we can increase the margin, we can make this part smaller, but we're going to end up making this part a little bit bigger because things that maybe had 0 value maybe now are going to be positive because they might be within the margin now. And it turns out that this formulation is equivalent to minimizing a particular loss function here where this loss function is the hinge loss, which is defined as the max of 0 and 1 minus the product of the true value and the predicted value. So to illustrate what this means graphically, let's say we have so if we want to minimize the number of misclassifications, that we would be looking at something like the 0, 1 loss, which suppose on our x-axis here we have the product of the true value y and our predicted value y hat. So if we're predicting values that are either negative or positive 1, this value will be either 1 or negative 1. And so if it's negative 1, then that means that our prediction doesn't match the true value, right? Because if they're both negative 1, it'll be positive 1. If they're both 1, it'll both be 1 too. So it kind of is going to when we plot the function, the 0, 1 loss will look like this. So say this is at 0, and then over here on our y-axis, this value is 0, and this is 1. However, for the hinge loss, it's going to look more like at 1, so for hinge loss, at this point to the right, everything is correctly classified because it's positive, because it's going to be the max of 0 and 1 minus prediction times the true value. So you can see here that the hinge loss is a convex relaxation of the 0, 1 loss. So it always has a greater value. And it's convex because if you take any 2 points on this line, the line that connects those 2 points always falls above the function itself. Whereas, say, on the plot for the 0, 1 loss, if you looked at this point and drew a line, not everything falls below the line. So that's not convex, so it's harder to optimize. And the hinge loss, the way that it's set up kind of shows that if you're correct, you have 0 penalty, and if you're wrong, the more wrong you are, the higher penalty you have. So that's the idea behind more heavily penalizing predictions that are way, way, way off. And in this case, when you have this soft margin SVM, you actually have more support vectors in that things that are within the margin become support vectors, and so are things that are outside of, or things that are incorrectly classified also become support vectors. So like here, this was a support vector anyway because it was on on the margin. This was a support vector because it was on the margin. But now this is misclassified, so it's going to be a support vector. That's misclassified, and that's within the margin, but still on the correct side. So that's about SVMs for just binary classification. But suppose we had, say, 3 different classes, and we wanted to classify. Can we use SVMs for that? So I'll draw a little picture. Suppose here we have some circles, some pluses, and some minuses. So we can see they're all kind of in different areas, and we should be able to somehow come up with some sort of boundary to separate them. Does anyone have any suggestions for how we can maybe modify the approach we took so far with the SVMs for this multi-class classification? Yeah? So what we kind of want to learn here is boundaries between all the different classes, right? So we're going to, well, yeah, we'll end up learning different boundaries. But what are some ways that we can formulate how we're going to find these different boundaries? A few of them are, you basically just take the same SVM idea we did before, but do it in a few different ways. So can anyone think of just a way that we can almost make this look more like a binary classification problem? Yeah?
You could do one class versus the rest.
Yeah, that's one thing you could do. So in the one versus all, maybe we would look at circles and want to differentiate them from everything that's not a circle. So if we looked at that case, here we might get a boundary that looks like that, right? And then for the minus signs, we wanted to separate them from everything else, get something that looked like that. And then for the plus signs, separate them from everything else, and get something that looked like that. So then when we got a new point, what we could do would be, so for each line here, we would learn the parameters associated with that boundary, the W and B. And then if we got a new point, well, first of all, does anyone have any suggestions for how we would decide exactly what class to assign a new point to? So say we've learned, we know the parameters for this line. This is related to the circle, so W circle and B circle, and this is for the plus sign, and then this is for the minus. So we've already learned all of these parameters by just doing 3 separate SVMs. So if we got a new point, say our new point was, I don't know, say that it's right here. How might we decide to classify this point based using the information we know about the decision boundaries we've learned so far?
Yeah, we can test against the 3 boundaries.
How would we test it against the decision boundaries?
We have W plus and B plus, so you can check for each of those lines, and whichever side it falls on, whether it's greater than 1 or lesser than 1.
So you're just looking to see whether, okay. So let's say on this one, we say that greater than 1 was on this side and less than 1 was on this side. So for this particular line, this point would be greater than 1. And then on this one, for the minuses, on this side is greater than 1, on this side is less than 1. So it's also greater than 1 for the minuses. So would we say it's minus or plus in that case?
Yeah, we can see the confidence of the result.
Yeah, exactly. So what we can do is we can calculate the W transpose X plus B for each of these values we learned for the decision boundaries, and whichever has the highest confidence, then we'll say it's in this class. Yeah, that's good. So that's a similar idea, kind of like how in logistic regression, when you're trying to predict a new point, you take the, you're basically looking at the probability that it's in each particular class and then choose the one that's the highest. In this case, this is a similar setup where we have this sort of confidence in our prediction, and that's how we can choose. Does anyone have, there are a couple other ways that we could go about doing this multi-class classification with SVMs. Does anyone else have a suggestion? There's another one that also kind of reduces it to multiple binary classification problems. Okay, well, in this first case, in the one versus all classifier, what we did was we kind of lumped everything else into one group, and that's how we created a separate binary group. But what if instead we just looked at all pairs of groups and learned a classifier between the two of those? So in that case, say we wanted to learn a boundary between the circles and the minus signs, we might get one that looked like this. So this is going to be circle minus. And then if we looked at the pluses and minuses, we'd maybe get something that looked more like this. And then, let's see, we'll have circle minus, plus minus, and then circle plus. We would get maybe one that looked kind of like this. Yeah. And so then how might we decide a final label for a new point in this case? So one thing that we could do here is that for a new point, we could train or look at what the value is for each of the three classifiers. Well, in this case, three. For each of the classifiers, say what side it's on, and then or say what class it belongs to for those two particular classes, and then put all the kind of all the classifiers to a vote, and then whichever one said that it was highest would be the class we ultimately assign it to. And then one last way that I wanted to talk about that we could handle multi-class classification. Well, first, does anyone have any thoughts on what it could be? Yeah?
I'm just wondering, is there one of these methods that's preferred?
I'm not sure. So, yeah, I guess, I mean, if you're doing it, it's worth trying multiple things, but I'm not sure what. I used an SVM once. I don't remember what I did for the final, for multi-class. I don't remember what it was. Might have been one versus all. I'm not sure, though. So another thing that you could do, this kind of extends the idea of SVMs beyond just binary classification. So the two ways we talked about before sort of reduce the multi-class classification problem to binary. But another thing you can do is maybe you want to learn these boundaries simultaneously. So in that case, you can set up a new objective function that is more about maximizing all of these margins in conjunction with one another while obeying constraints that things fall in their respective kind of portion of this instance space. But won't really get into that. So now I'm going to talk just a little bit about using kernels for support vector machines. So this kind of goes back to what I briefly talked about before, about how maybe if your data aren't linearly separable or even have a decent margin in the original feature space, maybe what if you transformed them to a higher dimensional space and you were they were separable in that space. So one neat way that you can do that computationally efficiently with SVMs is with kernels. The idea behind kernels is that, let's see, what do I want to look at? I'll erase this. Beautiful. Okay. So the idea behind kernels is that basically you just define a kernel function between two vectors that corresponds to a legal definition of a dot product. So if you're able to formulate whatever problem you're solving in terms of just dot products, then you can substitute in this kernel function and use that instead. So it turns out if you look at the dual of that problem there, we can write that as you want to maximize, let's see, negative 1/2 the sum of So here, this is an equivalent way of setting up this problem, but now we have these dual variables, alpha, that we're optimizing for. And you can see the only place that the x's show up is as a dot product with other x's. So in this case, if we have this kernel function, that is a legal kernel, we can substitute this kernel function in here, which is helpful because if you define this feature mapping implicitly, you don't even have to represent the higher dimensional feature space. You can just keep track of these dot products, which basically then is just going to be in terms of, or it's going to scale kind of with the number of data points you have and not the dimension of the space you transform it to. And in that case, you can substitute in the kernel value here. Like here it would be k, xi, xj, and then you're essentially working in this other feature space that you mapped your original data to. And here in this case, so this is for the This is your objective. Here we want to maximize it, and then while maintaining these constraints on the dual variables. And this is for the soft margin formulation. And actually, if you have the hard margin formulation, then this part goes away, the upper bound on the alphas. But generally, I feel like it's more useful to do the soft margin version, because then at least you can find something. Whereas if for hard margin, if your data aren't linearly separable, then it just won't return anything. So here in this setup, again, well, not again, but once you know what once you've maximized for your alpha, you can express W as the sum of alpha I in this way. So one thing that's helpful here is that the alphas are non-zero only for your support vectors. So like we talked about before, typically a very small fraction of your samples are actually going to be support vectors. So those are kind of the only, in this case, since the alpha corresponding to the support vectors are the only non-zero ones, so those are the only ones you really have to store. And from that you can calculate all the parameters that you need to, and then make predictions on your new values. Yeah, so if you were to then use a kernel here, when you solve for the optimum here, instead of your particular x's, you would just substitute in phi of x. And we talked about a few different kernel functions in class, like linear, polynomial, Gaussian. And then one nice property of kernels is the way that you're able to, there's some operations that you can perform to essentially like combine different kernels into another kernel. Well, depending what operations you do, you know that it's the result is still a legal kernel. So you have some practice problems with that on your homework. And then, does anyone know what time it is? 7:40. Okay, I think we have time for that. I was going to talk about Lagrange multipliers for a little bit. So in the homework, you have one question that requires the use of Lagrange multipliers. It's actually an extra credit question, so you don't strictly need to know how to do them, but I think they're helpful. Let's see. So suppose we have an optimization problem. We want to minimize or maximize some function subject to some constraints. So ordinarily, if you just had a differentiable objective, what you would do is differentiate it, set it to 0, and then solve for the optimum value for whatever you're looking for. But that's in the unconstrained case. So what if you had certain constraints that needed to be true at the optimum value that you found? So we'll set up a problem here where suppose you have a line, and we'll say it's defined by W transpose X plus B equals 0. And then say you have a point over here. And we'll call this point Z. And what we want to find is the distance between this line and this point. So one way we can set up this problem is, so let's say that everyone agree, right, that the shortest distance between these two is going to be where this forms a right angle, right? So we'll call this point where it meets, and we say we're going to define that as our distance. We'll say that, call this point a particular x here. And what we want to do is minimize the distance between x and z. And again, we'll square it to make it easy to work with, subject to the constraint that x lies on this line. Because if you can choose any x, right, the one that's going to minimize this value is if you say x equals z, because then the distance is 0. But we're looking for something on this line. So when we form what's called the Lagrangian of this particular optimization, it takes our objective function and then a Lagrange multiplier times the constraints that we have. So in general, or I guess in general, if you want to minimize some f of x subject to, maybe you have constraints that g of x is 0 and maybe h of x is less than or equal to 0. What you're going to do from that is you can form the Lagrangian. Will be of x and then, which is going to be your objective value plus some Lagrange multiplier times each of your constraints. So in this case, if we wanted to form the Lagrangian, let's see, we'll just say this is one. It would be our objective function here plus some Lagrange multiplier times this constraint. And then what you can do from this point is differentiate the Lagrangian with respect to whatever you're optimizing for, set that to 0, and kind of proceed as you would normally. Although, okay, yeah, you're going to need to find the value of your Lagrange multiplier as you go through this process. So let's take the partial derivative of the Lagrangian with respect to x, because we're trying to minimize over x. So if we take the Lagrangian here, or sorry, the derivative of the Lagrangian with respect to x, we'll get it's x minus z minus lambda times w. And then we'll set this to 0 and solve for the optimal x. So what we'll get there is that x star is going to be lambda w plus z. So we found an optimal value for x, but it's in terms of lambda. So what we need to do is figure out what lambda is now. However, we know that this constraint is going to hold for our optimum value of x. So we'll just substitute this value of x and over to the constraint. So we know that from our constraints, w transpose x star plus b equals 0, which means, let's see, w transpose lambda w plus z plus b equals 0. So we'll get that lambda equals negative w transpose z plus b over w transpose w. And then if we substitute this value of lambda back into our optimal value for x, we can get our final result. And that's enough of Lagrange multipliers for you to solve the constrained optimization problem that you need to set up for the extra credit on the homework. Does anyone have any questions about this or anything? So I don't know if anyone's looked at the homework yet, but the part that deals with Lagrange multipliers, it's part of you're running the expectation maximization algorithm for categorical mixture models. So in class, Tom went over Gaussian mixture models. So this is similar. You have what you observe is a collection of samples drawn from different distributions. So in order to model that, we assume there are these hidden variables that indicate which distribution a particular observation came from. And the case in the Gaussian mixture model was once you knew what hidden distribution you were going from, it was normally distributed. In the categorical mixture model, your observations are all drawn from categorical distributions. So the idea there is, say you have k different possible values it can take on, and the way you specify that is with a probability vector that says the probability it would be each value of that class. So because it's a probability, all of its values have to sum to 1. So that's the sort of constraint that you'll have for that particular question. All right, if there are no questions, I guess we're finished now. So have a good night. And the homework was released earlier today, so have fun with that. You have until Friday to work on it.